about very important process, which is the matching between the turbine and the compressor and the engine in case when we have a turbocharging. And at the design stage, how we can design the turbocharger, design the turbine, design the compressor in order to match the operation of the engine in this case. Last time we talked about the difference between turbo and supercharger. We said the supercharger, we have a compressor. This compressor actually compresses the air to have more air to the engine. Then we can increase the fuel and then we can increase the engine. But this compressor, in case of supercharger, this compressor take part of the engine power, which is through the crankshaft, through a gear connection. We can drive this compressor. So the main drawback of the supercharger is that actually it just consumes part of the engine power because the compressor is driven actually through the crankshaft. On the other hand, we have the turbocharger in which we utilize the blow down energy when the exhaust valve open. Then we can actually recover the heat out of the exhaust gases to drive a turbine, and this turbine can drive the compressor in this case. And that's why the turbocharger is more efficient than the supercharger. But we have a problem with the turbocharger is that actually at part load condition or at lower RPM, the mass flow rate of the exhaust gases is not enough to generate enough pressure ratio across the turbine, not enough to generate actually a power that is required to drive the compressor and generate the required pressure ratio in order to drive actually a significant boost of mass flow rate of air. Then we can have significant boost on the power. So at lower RPM, the mass flow rate of the exhaust is very low, so the turbine in this case cannot generate enough power to have a boost through the turbocharger system. So usually turbocharger, its operation, we can benefit the use of the turbocharger actually at from medium to high load, we can have an effect of the turbocharger. Also, the turbocharger needs some time. There is a delay, there is a lag. So once you press actually on the accelerator pedal, if you have turbocharger, it will take a little bit some time until actually you get a response and the car actually starts speeding in this case. This is unlike the case of supercharger. Supercharger just takes the power from the crankshaft. So even at lower speed, when you just click the accelerator pedal, try to accelerate, then in this case you will find the car is responding faster in this case. Okay. In this case, if we look at the turbocharger, if you look at any turbocharger, we have a compressor. This compressor just takes the air, the atmospheric air, let's say at state number 1. So we have a given mass flow rate of air in this case. The function of the compressor, it will raise the pressure actually. Let's say the air will be leaving at point number 2, and it will actually provide a mass flow rate of air to this engine. This air will be just delivered to the engine, to the internal combustion engine in this case. And this engine will decide about the angle, the crankshaft angle at which actually the exhaust valve will be opening. So here at point number 3, the temperature here is the temperature T3, which is the temperature of the exhaust gases. The temperature of the exhaust gases when the exhaust valve open. So this is at the exhaust valve opening. So this temperature will be decided by the electronic control unit inside the engine, which is actually controlling the operation of the engine, will decide at which angle we should open the exhaust valve. Then in this case, the temperature of the gases will be T3, and the pressure of the exhaust gases, let's say, will be P3. This pressure and temperature of the exhaust gases will be delivered to the turbine. So here we have a turbine. It will expand through this turbine, and the exhaust gases will be leaving out. Let's say actually the exhaust gases are leaving at point number 4. This turbine here is connected to the compressor on the same shaft. So the power out of the turbine will be just driving the compressor in this case. Okay. But in this engine we have air is coming in plus the fuel. Then we burn air plus fuel. Then actually the mass of the exhaust gases, mass flow rate of the exhaust gases should equal to what? Mass of air, mass of the exhaust gases, the mass of the flow rate through the turbine is equal to the mass of air development plus actually the mass flow rate of the fuel. The mass flow rate through the compressor is equal to the mass flow rate of air. The pressure ratio through the compressor, which is B2 over B1, we call it the compressor pressure ratio, which is B2 over B1. This compressor pressure ratio will decide about the increase in the pressure B2. And based on that, it will decide about the intake density. to the engine. The density at the intake manifold will equal to pressure at the intake manifold, which is P2 divided by R multiplied by Cn in this case. So if we are able to raise this pressure at the intake manifold of the engine through the compressor, then in this case we can raise the mass flow rate of air. And based on this mass flow rate of air, the engine will decide about the corresponding mass flow rate of fuel that will achieve a certain value of fuel to air ratio. We said that a gasoline engine, especially, is working also almost at a stoichiometric condition, almost at lambda equal to 1. So the actual fuel to air ratio almost is fixed at all load, and it is almost a ratio of 1 of 14.6. This is almost the fuel to air ratio for a gasoline engine under a stoichiometric condition, under lambda is equal to 1. So depending on the incoming mass flow rate of air, the engine will decide about the mass flow rate of fuel, and also the engine will decide when to open the exhaust valve, at which temperature the exhaust gases will be leaving, and also at which pressure P3. Then the gases under high pressure P3, the exhaust gases will be expanding through the turbine to drive the turbine. Then the turbine can drive the compressor in this case. So the mass flow rate through the turbine is the mass flow rate of the exhaust gases, which is the mass flow rate of air plus the mass flow rate of fuel coming through the engine, and the pressure ratio should go through the turbine, which is P3 divided by P4, which we call it actually the turbine pressure ratio. So the angle at which the exhaust valve should be opening will decide about the pressure P3. That means actually it will be deciding about the pressure ratio across the turbine, because the pressure P4 is almost the atmospheric pressure. The exhaust of the turbine is to the atmosphere. However, the turbine is connected to the exhaust system of the car. After this turbine, the flow should be going through the exhaust tailpipe, and the exhaust tailpipe, it may result in little bit a kind of back pressure on the turbine. So usually the pressure P4 is not actually P1 is P atmosphere, because the compressor takes the air from the atmosphere. But usually the turbine just exhausts the flow into exhaust tailpipe, which has a small diameter. So it will result in a kind of back pressure on the turbine. So this pressure P4 will be a little bit greater than the atmospheric pressure. But we can assume it atmospheric pressure. So the exhaust is the angle of the crank angle of the engine at which the exhaust valve will be opening will decide about P3, and P3 will decide actually about the pressure ratio across the turbine, which will decide actually about the power of this turbine HVAC. And the power of the turbine HVAC should equal to what? They are on the same shaft. What is the relation between the power of the turbine and the power of the compressor? It should be what?
Equal.
It should be the same. But here we have a crankshaft. So whenever we have a rotation, so we should have a friction. Friction, that means we have to have mechanical energy. So the first matching between the turbine and the compressor is that the work of the compressor, the power required to drive the compressor, it should be the same as the power of the turbine, but we have to multiply here by the mechanical efficiency of this shaft, of the turbocharger, because there is efficiency for transmitting the work of the turbine to drive the compressor. Due to friction, we should have some minor losses. The size of the turbocharger is small, so usually this mechanical efficiency is almost very close to 100%. But as they are working on the same shaft, so that means the power of the compressor should equal to eta mechanical multiplied by the power of the turbine. But as they are working on the same shaft, that means actually the RPM of this shaft for the compressor is equal to the RPM of the turbine. And this is a This is matching between compressor and turbine. What about the engine? The whole system should be matching, so we should not have an error. So we have to decide about the operating condition through actually all loading condition. So the car at low speed or high speed, medium speed, low load, part load, full load. We have to decide about all of the operating point under all of this point. And each operating point has to have matching between compressor, matching between the engine, and also matching with the turbine. The three of them has to be matched together. Otherwise, the turbocharger actually will result in operating problems, so many operating problems. So we have to decide about the operating point at all load And then we have to go to the ECU, the electronic control unit of the engine, and we have actually to store actually all of this operating point. So when you are running your car, when you press on the accelerator pedal, then in this case the ECU actually will decide about the amount of air needed. Also it will be, the value is stored. This is actually if the amount of air is equal to this value based on your press on the accelerator pedal, the ECU will decide about the amount of fuel. And also, the operating point, it has to be recorded actually at which crank angle we have to open the exhaust valve, because this will decide about the pressure ratio across the turbine. That means it will decide about the power of the turbine, and that will decide about the power of the compressor. Power of the compressor will decide actually the pressure ratio of the compressor, and this pressure ratio will decide about the mass flow rate of air. So it's a kind of closed loop, but we have to match the three of them. And we have to record actually all of these operating conditions, in this case for proper operation of the turbocharger system. So the first matching equation that we have, the power of the turbine should equal to eta mechanical multiplied by the power of the compressor equal to eta mechanical multiplied by the power of the turbine. And as they are actually connected on the same shaft, so they should have actually the same running RPM in this case for the turbocharger. But please make difference, Shabab. This shaft of turbocharger is running about 100,000 RPM. 100,000 RPM. The crankshaft in the engine, if you look at the tableau of your car, you will find actually the maximum RPM may be about 8,000 RPM. And usually while driving your car, usually the RPM will be around 2,000, 2,500 or something. Okay? So you have to differentiate between the crankshaft revolution and the spin revolution here, which is very fast because we have dynamic design, dynamic blades between the compressor and turbine, and it is separated from the engine. This is unlike the case of supercharger. Supercharger, this compressor takes its power from the engine here. So its RPM in case of compressor, for the compressor in case of supercharger, the RPM cannot be actually more than 10,000 RPM. We can take the RPM of the engine, try to reduce the gear size to increase the speed of the shaft of the compressor, but it can be increased the maximum to about 10,000 RPM. This is in case of supercharger. But in case of turbocharger, you can see the RPM is more than even 100,000 revolution per minute in this case. But what are the limitations that you have here for using a turbocharger or supercharger? Just please keep in mind point 1 and point 2. Point 2 is at the exit of the compressor, point 3 at the exit of the engine and at the inlet of the turbine. Okay, I will use this terminology 1, 2, 3. So just keep in mind this. But what are the limitation for using turbocharger? Do we have limit like for the case of gasoline engine? Is it allowed to use turbocharger under all conditions without any limitation for the pressure ratio across the compressor and for the mass flow rate? Can we increase the mass flow rate for infinity? So can be operated in this case?
No, we need to keep it to make sure that the air that gets into the engine is near stoichiometry.
Near stoichiometry, and also Shabab, there is a limitation, very important limitation in the gasoline engine that we cannot have if let's say if you have mass flow rate of air is too high, then the mass flow rate of fuel will be increased. That means in this case the power, we call it the brake power or the shaft power for the crankshaft, will be increased in this case. But before this brake power increase, we should have the indicate power should be increased in this case, which is the power inside the piston. That means if we have higher mass flow rate of air and the higher mass flow rate of fuel, so the maximum pressure within the cycle and the maximum temperature in this case will get too high. But what about gasoline engine? Do we have limitation for maximum temperature and maximum pressure?
Yes, we have a limitation.
What is the limitation? Limitation for maximum temperature, Shabab, is what? Is the engine knocking, because we may have self-ignition of the fuel, so we cannot increase this mass flow rate of the fuel, of the air, too much in case of gasoline engine. That means the pressure ratio, the compressor pressure ratio, should have a limit. This limit يعني is almost about 3.5. So that we can result in mass flow rate of air. It's okay, we have a boost, we have increased. The mass flow rate of fuel will be increased. The indicated bar يا شباب, let me just show it again. يعني this chapter I should have يعني given the chapter of performance before, because I have different terminology here that I should have clarified earlier. But anyway يا شباب, this is the engine. When you burn the fuel inside the engine here, you generate heat. This heat actually at high pressure and high temperature will press the piston down. The power that press the piston down, we call it the indicated power. This indicated power, شباب, that is represented on the PV diagram by the cycle on the PV diagram. If you remember, we said the cycle is actually, this is the network. The network. The power or the indicated power is equal to the work net multiplied by the mass flow rate. So this network, يا شباب, is the indicated work. As we have said actually in the last chapter, for the engine cycle, we have drawn the PV diagram for all of the cycle, and we said the net area, actually the network is represented by the area contained by the cycle. This network, يا شباب, we call it the indicated work or the indicated bar. Indicated bar is equal to the indicated specific work multiplied by mass flow rate. So the indicated power is the power generated inside the cylinder, which push the piston down. This piston, يا شباب, here is connected to a crankshaft through a connecting rod. Then we can transfer actually this reciprocating motion in the piston. We can convert it to angular motion on the crankshaft. The power on the crankshaft, يا شباب, which is shaft power, we call it the brake power. And that should be the final outcome of the engine. Brake power is equal to actually the torque multiplied by omega. Torque multiplied by omega, which is omega here, يا شباب, not the work, which is 2 by n over 60. And n is the revolution per minute in this case. And the initial input here, يا شباب, to the engine is what? The fuel energy, which is equal to what? Mass flow rate of fuel multiplied by the heating value. So first of all, يا شباب, at the engine intake, the power is the fuel energy, which is the chemical energy of the fuel. By having the combustion, heat transfer will be generated, and the work will be generated to move the piston. This power that moves the piston, we call it the indicated power. Part of this indicated power is lost in the friction losses through the piston movement up and down. We should have friction here that should be converted to heat, and this heat will be transferred to the lubricating oil in this case. Also, there is friction through this connecting rod at the junction and the connection here for the piston and the crankshaft. So we have friction loss power in between. And at the end, we should have the brake power. That means, you should have the brake power, which is the crankshaft power, should equal to the indicated power generated inside the piston that moves the piston down, minus the friction loss power in this case. Okay, so this is, the difference between brake power and the indicated power in this case. So there is a limitation for the operation of the turbocharger, that the compressor pressure ratio should not be increased too much, so that actually we don't increase the maximum temperature or the combustion temperature within the cycle to higher level. And also there is a limitation of the pressure, higher pressure within the cycle, which will affect what? There should be a limit on pressure. This limit on pressure will decide actually about the material strength. So if you want to drive an engine at very high pressure, so you have to design this engine to be able to withstand this high pressure. So there is a material strength issue, which usually in case of diesel engine, because diesel engine usually works at very high pressure. So heavy, in this case, we have to use heavier diesel engine in this case in order to be able the high pressure generated in this case. And usually, if you are using even a turbocharger with a diesel engine, that means this high pressure will be increased more. That means the weight of the engine will be increased, because we have to design the material in order to be able to take this pressure. Okay, but there is a limitation, another limitation in gasoline engine regarding the temperature. We should not raise the temperature too much, so that actually we can avoid the engine knocking in this case. Also, there is a limitation on the pressure. As I told you, we have a limiting number of brake main effective pressure. Brake main effective pressure is the brake power divided by the displacement volume. When we like the indicate main effective pressure, we have defined the earlier, if you remember in the engine cycle, we have defined in the indicate main effective pressure as the indicated power divided by the displacement volume. Indicated power, شباب, we call it as work net. As I told you, the indicated power is the net work that we can get actually by the representation on the PV diagram, which we have considered in the preceding chart. We call it the indicate mean effective pressure. Any mean effective pressure, شباب, is equal to the corresponding power per unit displacement volume. Usually in the internal combustion engine, we are interested more in the brake mean effective pressure, because brake mean effective pressure considers the brake power, which is the final outcome of the engine, which is equal to torque by omega. But there is a limitation also on the brake mean effective pressure, so that actually we can design the material to have actually we can design the engine with a material that can withstand this high pressure. So there is a limitation for the turbocharger system that the brake mean effective pressure for the engine should not exceed a value of 22 bar in this case. Okay, so this is another limitation. Third limitation, شباب, is the high temperature, as we said, and the high pressure. High pressure, there is a limitation on the material strength. High temperature, there is a limitation on engine locking, and a limitation on what as well, شباب? When we have high combustion temperature, if it is too high. So what will happen as well inside the combustion chamber? We may have self-ignition for gasoline engine, but what else? حسين؟ حسين بنوير؟ حسين؟ Listen, do you have an idea about that? So what will happen if we have high combustion temperature? We said knocking may happen, and also شباب, at high combustion temperature we may have NOx emission. As we said, nitrogen, N2, can be dissociated to N plus N, and it can recombine with oxygen, so it can form NO and NO2. And those are actually a kind of NOx emission. And we need to avoid actually the engine emission in this case. So there are some limitations, شباب, on the turbocharger. We cannot say I will be using turbocharger anyway. I can increase the mass flow rate of air to whatever I want, increase the mass flow rate of fuel to whatever I want, and then I can get more power of the engine. No, the engine itself has some limitation. Okay, you cannot increase maximum pressure because you have to design the engine to withstand this high pressure. You cannot have also very high temperature, because in case of gasoline engine, you will have engine knocking, and the engine knocking will just destroy the whole engine. So you have made a turbocharger to increase the engine power, but it resulted in adverse effect. You left with engine knocking in this case. Okay. That's why, شباب, we said usually the turbocharged engine have shorter lifetime. So if you have a car that is turbocharged, it should have shorter lifetime, because this engine, شباب, is working at high pressure, burst pressure, which is more than the normal pressure that it should be working on. High pressure, high temperature combustion, that means actually its longevity will be reduced in this case. But let's look, شباب, at the matching process, and we need to develop as a mathematical model so that we can match and get the operating point, proper operating point that can match between turbine, compressor, and also the engine in this case. We have to match, actually the operating point should be matching between the three of them. If you look at the compressor, شباب, the pressure, output pressure of the compressor, usually it is function of different parameter. It is function actually of the temperature, RT1, based on the ideal gas equation of state. Function also of the atmospheric pressure, V1. If we have this turbocharger, we put this turbocharger at the top of the mountain. Top of mountain, that means actually, in this case, the atmospheric pressure will be reduced. So this is also another parameter. It is function of the RPM also, function of the dynamic viscosity of the air, function of actually the specific heat ratio for the air, which can be changed while the compression process. And we do have also some geometric parameters. Geometric parameters for the design of the compressor. We said the design of the compressor should have take the shape of the diffuser so that we can result in increase in pressure in this case. So the output pressure of the compressor should be function of many parameters. You can consider, I don't know, do you have an idea about the pi theory? Do you have an idea, Shabab? To get all of these parameters non-dimensionalized? Have you went through it?
No, I don't think so.
So that should be in fluid mechanics, شباب. We can just, if you have one parameter that depends on many parameter, we can recombine this in a dimensionless form. If we did this through a by series, that is not our subject here, then in this case we can get a dimensionless form that can give us a relation between the pressure ratio, which is a dimensionless parameter, as function of a dimensionless parameter of the mass flow rate, which is m dot multiplied by the square root of the inlet temperature T1 divided by the pressure B1, and also another dimensionless parameter, which is the engine, the shaft RPM for the compressor divided by the square root of the inlet temperature. And based on those parameters, we can generate what's called the compressor map. So this is the compressor map. If you have any compressor, not only for a turbocharger, if you have a compressor for any application in the industry, you should have actually the manufacturer should give you the compressor map. This compressor map will give you the ratio of the pressure ratio across the compressor, B2 over B1. This is just a kind of map that will give you the value of the pressure ratio, B2 over B1, as function of the axis here is a mass flow rate in the dimensionless form, multiplied by square root of Q1 divided by the pressure B1. And this map will give us here the operability of this compressor at different operating RPM of this compressor. This is actually, each of this line represent a value of n divided by a square root of T1. Okay? So, and at each line, at each operating speed, there is a minimum value for the mass flow rate that can be actually taken by this compressor. And all of those points connecting the minimum allowed mass flow rate of air through the compressor, this line should form a line, and this line we call it the surge limit or the surge line. So at any operating speed of the compressor, the mass flow rate should be not less than a given value. So what will happen at this value of the mass flow rate of air is less than this value? That means in this case it will happen actually a flow surge or flow reversal. The flow will be reversed in this case, and the whole system will be stopped from the operation. But let's look at actually this idea, Shabab. Do you have an idea, Shabab, about the computer surge, the compressor surge? Anyone can explain to us how it happens? So the compressor. Yes, Al.
What is it again?
Do you have an idea about the compressor surge when it happened? We said it happened when the mass flow rate of the compressor coming to the compressor is less than a given value. In this case, flow reversal will occur inside the compressor, and the whole system will stop in this case. So if you look at this map, Shabab, you are allowed to work at any point, at any given RPM, but there is a limit for the mass flow rate. We cannot drop actually the mass flow rate at a given value. Because in this case, Shabab, the angle of attack, if you look at the compressor, Shabab, it's an aerodynamic. It looks like the aerofoil. The aerofoil actually, which is like the wing of the airplane. If you look at the wing of the airplane, so the air should be coming with a given angle here. This angle, Shabab, we call it the angle of attack. Okay? Angle of attack. If it is coming in this direction, so the air will be moving through the aerofoil smoothly, and in this case, some recirculation is created actually downward of this aerofoil, and that's why actually the pressure here will be low, and the pressure will be built up here. Sorry, the pressure here will be low, and the pressure here will build up, and that's why we should have a kind of lift. That's why the airplane will be just flying due to the effect actually of the difference of pressure on above and below the aerofoil, which should be actually, if you look at the airplane, this is the size of the wing of the airplane. It's just something like this, but it takes the shape of aerofoil. So the air is coming with a given angle of attack. Let's say it is theta, angle theta. It comes here, so the flow of air just go in streamlines here, and it creates some pressure losses because here the distance here that the air should be moving. If you look at the aerofoil design, this distance is longer. So that means the air should be moving with higher velocity. at the top part of the aerofoil. That means the pressure will be reduced here. Up here, look at the air going from here. So this distance يا شباب from the inlet of the aerofoil at the outlet until the outlet, this distance is small. That means the velocity will be low. And the pressure will build up actually below the aerofoil. And that's why we should have difference in pressure, and that's why the airplane should be moving. The same idea شباب for the compressor. Compressor is consisting actually of fixed blade plus moving blade. The function of the fixed blade is to take the air coming at a given angle of attack, and then it will be leaving, and this air will be delivered actually to a moving blade in this case. If you look at the axial compressor, this is the axial compressor. This is the shaft. The axial compressor we have here moving blade attached to the impeller, and before this moving blade, each row of moving blade, we should have row of fixed blade attached to the case. The function of the fixed blade here is just to direct the air to hit the moving blade at a given angle. Okay? So if the air is coming actually to the fixed blade takes the shape of aerofoil. Okay? If the air is coming with improper angle in this case, so let's say the angle of attack has been changed to another location. So what will happen to the flow in this case? So let's look at this. This is يعني شباب a kind of very interesting يعني part if you want to look at. So this is يعني the aerofoil. The aerofoil. Let's say the air is coming at this angle. At lower flow rate, usually the angle of attack will be changed in this case. But if flow is coming to the fixed blade with this angle, so what will happen to the flow يا شباب? The flow will be moving in this direction. So in this case, flow separation here and recirculation will be created. Recirculation will be created, that means the pressure will be raised in this case. But the flow should be coming in this direction. But due to the high pressure here, and due to the flow recirculation, the flow will be reversed in this case. And it will be leaving the compressor. Instead of coming into the compressor, it will be leaving the compressor. Due to the recirculation in this case, the flow recirculation. And under this condition, شباب, we call this case actually the compressor surge. Compressor surge will cause actually what we call the compressor stall. Compressor stall, that means actually the compressor has stopped working. So the stall is due to actually the flow surge. So you may look at this video شباب. So let's look here. So here شباب is the compressor. This is the axial compressor used in an airplane engine. We are not talking about يعني it is the same case يا شباب. Airplane, we have a compressor and we have a turbine, and in between we have combustion chamber. Here we are talking about turbocharger for internal combustion engine. So instead of the combustion chamber, we have the internal combustion engine, but it is the same way. But look here, the compressor consists of fixed blade followed by a row of moving blade. So the function of the fixed blade is to direct the flow. But let's look here what will happen if the angle of attack in this case is changed.
The rotor blades have an airfoil cross section.
So here is شباب, this is the fixed blade, as you can see. So look here. So you can see شباب. So when the angle of attack at lower flow rate, the flow will coming with different angle of attack. So some flow recirculation will be created here, and the back pressure will be created, and flow stall in this case. So what will happen شباب if we have bird strike? Some bird just get into the engine in this case. So what will happen? It will cause actually surge. The angle of attack of air will be changed. So that's why the engine will be stopped in this case. We will have angle of attack of aerofoil will be changed. We'll have flow reversal. And in this case, the whole system with the engine will be lost in this case for the airplane. So anyway, Shabab, you can look at the remaining of this video, okay? It's an interesting one. Please look at it. So this is the meaning, Shabab, of compressor surge. But this is, Shabab, yani the compressor map, as we said. It will be provided with the compressor for any application. The manufacturer should give you this map that will provide you the pressure ratio across the compressor at a given mass flow rate, but usually they use a dimensionless form. It will be M dot multiplied by T1 divided by B1 as function also of the dimensionless RBM, which is N divided by the square root of T1. Like this also, Shabab, for the turbine. In case of the turbine, any turbine also we should have a turbine map. This map for the turbine will give you the ratio also M dot, but by multiplied by the square root of the inlet temperature to the turbine, we call it T3, divided by the inlet pressure P3. We say the Shabab P3 and T3 are the value of the pressure and the temperature when the exhaust valve open for the engine, the exit of the engine. And here's the pressure ratio of the turbine, which is P3 divided by P4, and a different value, Shabab, of the running RPM, N divided by square root of T3. Different value here, they can give you actually the operating. So if you have, let's say, through the turbine, a given mass flow rate at a given RPM, then in this case, we can calculate the pressure ratio of this turbine using this map. Also in the map, Shabab, you will find some line are representing actually the efficiency of the turbine, the isentropic efficiency of the turbine. Like here also for the compressor, you will find some line giving you at each point the isentropic efficiency for the compressor. Okay. But here for the turbine and for the compressor, let's derive, Shabab, a mathematical formula by which we can match both of them, turbine and the compressor. This is, Shabab, at the design stage. Before designing the internal combustion engine, if you are to work, inshallah, with let's say any car manufacturing company, and you are required to design a turbocharger system in order to match with a given engine to boost its power. So those this process, Shabab, if you look at it on the Molière diagram, HS diagram, this is a compression process at point 1 and leaving at point 2, let's say 2S, which is the isentropic exit condition if the compression process is isentropic. But usually we have an isentropic efficiency. Usually it is very close to 100 because we don't have much heat losses in the compressor. So we reach here point 2 actual if the process is not isentropic. So the isentropic efficiency of the compressor, Shabab, is equal to the work dot isentropic divided by work dot actual. This is yani from 203 at the early beginning of this. Yani, I think thermodynamic, Shabab, is the first course in mechanical engineering. So this was part of it, how we define the isentropic efficiency of the compressor. It is the ratio between the isentropic work from point 1 to point 2S to the actual work from 1 to 2 actual. And based on that, Shabab, we can define the actual work as one of the isentropic efficiency of the compressor multiplied by the isentropic work. If you apply the first law of thermodynamics for a compressor, Q minus work will equal to delta H. We don't have heat transfer, so work will equal to delta H, and delta H will equal to MCB multiplied by delta T. Based on the ideal gas model, we can replace delta H by CB delta T. So the isentropic mass flow rate of air, the isentropic actually work will equal to mass flow rate of air multiplied by CB of air multiplied by the temperature T2S minus T1. This is the isentropic work. This is the actual work, and the ratio is the compressor efficiency in this case. But we can say work dot of the compressor will equal to 1 of the isentropic divided by the isentropic efficiency of the compressor multiplied by M dot air, CB air. Let's take T1 as common. We will have T2S over T1 for an isentropic process equal to B2 over B1 to the power T air minus 1 over the T air. T air, Shabab, is the specific heat ratio of air minus 1. And this is how we can calculate the compressor work in this case. Right, what about the turbine? Is it clear, Shabab? I'm just going a little bit fast with this part, so you have an idea about this part. You remember that, okay? Right, let's move to the turbine and let's develop another relation by which we can calculate the power of the turbine. So in case of the turbine, if you look at the pressure, the Molière diagram, HS diagram, the process through the turbine is expansion from the pressure B3 up to pressure B4. So let's say this is point 3. If this expansion is isentropic, so it will be leaving at point 3S. S which means isentropic, but usually we should have some heat is lost. So in this case, the process will be result actually in increase of the entropy. So as we said, for any adiabatic system, based on the second law of thermodynamics, delta S should be a positive value. So that means point 2 should be actually in the direction of the increasing of the entropy. For the actual process, we should have some losses, just should be converted to entropy generation and the entropy will be increased. But anyway, in this case, the efficiency of the turbine, the isentropic efficiency is equal to the actual work divided by the isentropic work. Or we can say the power of the turbine actual should equal to the isentropic efficiency of the turbine multiplied by the isentropic work. Isentropic work is the mass flow rate through the turbine. Mass flow rate through the turbine is equal to what, Ashibah?
Mass flow rate of air.
Plus what? Plus mass flow rate of fuel. Because turbine takes the exhaust gas from the engine, which is mass flow rate of air plus mass flow rate of fuel, multiplied by CB gas, multiplied by T3 minus T4S. 4S, which is at the exit isentropic condition. So that should equal to the efficiency of the turbine multiplied by mass flow rate of air plus mass flow rate of oil, CB gas. Let's take the temperature T3 as common. It will be 1 minus T4 over T3. T4S, this is 4. Okay, T4S over T2, which is isentropic process, it will be B4. Will be T4 over T3, so this will be actually B3 over B4 to the power K gas, K which is a specific heat ratio but not for air. For the compressor it is K for air, specific heat ratio for air. Here we have the gas which is exhaust gas fuel plus air, it will be K gas minus 1 divided by K gas in this case. And this is how we can calculate the power of the turbine, okay? But we said this power of the turbine should equal to what, Shabab? The power of the turbine should equal to what, Shabab? The power of the compressor. The power of the compressor, this one should equal to the power of the turbine, but multiplied by what? Multiplied by eta mechanical. So we have to multiply this term by eta mechanical, and we can equate it actually to this term. So the work of the compressor will equal to eta mechanical multiplied by the work of the turbine. If you divide here this equation by mass flow rate of air, so this term will be 1 plus mass of fuel divided by mass of air. It will be the fuel to air ratio in this case. This term B3 over B4, we call it the turbine pressure ratio, the pressure ratio across the turbine. And this term is the compressor pressure ratio. We don't know all of this value. We don't know the fuel to air ratio at this point. We need to match. We don't know the fuel to air ratio. We don't know the turbine pressure ratio that is required to generate a given compressor pressure ratio. So we don't know all of this value. We divide it by mass flow rate of air, so this term will be 1 in this case. So now, Shabab, we have resulted in an equation, matching equation, that is function of fuel to air ratio, function of turbine pressure ratio, function of compressor pressure ratio, function of the temperature T3, at which the valve will be opening, the exhaust valve when it opens. This temperature in this case will be T3. So we don't know actually all of this value. So we have 4 unknown in this case actually in this equation. And we have another equation for turbine and compressor that the RPM of the turbine should equal to the RPM of the compressor. And this is, let's say this is equation number 1. That should be equation number 2 in the matching process. Right? What about the engine itself? We said the engine will be deciding about what, Shabab? Engine will be decided about which of those parameters? Fuel to air ratio, and it will decide about what?
The temperature.
The temperature T3 at which the exhaust valve should be opening in this case. So we should do matching. So let me just set here. So we should do this matching process. So here what I said, we got this equation until we get this equation. This equation, شباب, will give us the turbine pressure ratio as function of fuel to air ratio, we don't know, function of T3, the temperature of the exhaust gas leaving the engine when the exhaust valve open, we don't know also, function of the compressor pressure ratio. All of these are unknown. Type and have another equation which is the RPM of the turbine should equal to the RPM of the shaft of the compressor in this case. And we have to do a matching exercise in this case in order to get the proper operating point that can match between the compressor to decide about the pressure ratio across the compressor and the mass flow rate to the engine. And also this point should match with the mass flow rate and the brake power out of this engine. And it should result actually the engine will decide about when to open the exhaust valve so that we can get a temperature T3 and the pressure B3 that is higher than the required pressure ratio across the turbine, so that we can make sure that the turbine will be able to generate enough power in order to drive the compressor to give enough amount of air to match this point. So the engine, شباب, the exhaust valve, and this is the idea of the matching exercise. This exercise is done in order to determine the angle at which the exhaust valve of the engine should be opening, so that we can calculate the value of B3 and the T3. And then in this case, the ratio between B3 and the B1 should be greater than the turbine pressure ratio, the required turbine pressure ratio, in order to drive the compressor in this case. And we do this matching, شباب, at the design stage of the engine in order to make sure actually that the operating point will be matching the three devices, compressor, turbine, and the engine, so that we can avoid, شباب, we can cover wider range of operating condition. As I told you, all of this operating point will be stored on the engine ECU. And when you press on your accelerator pedal, there is a signal that is generated and it will be sent to the ECU and it will decide about all of these parameters. Okay, so the idea at the design stage is to design the compressor and the turbine and the turbocharger system to match all of the operating condition of the engine in this case. Without having actually the turbocharger is very weak, just releasing actually very low pressure ratio across the turbine, and it will release actually very low air flow rate actually to the engine, even it may be less than the case of naturally aspirated engine. So this may happen in case of turbocharger. So we need to avoid this. Also, it may result in a very powerful turbocharger. And this very powerful turbocharger, that means we have to use the wastegate in order to bypass some of the exhaust gases to the surrounding without actually taking benefit of this exhaust gas power. So we just need to avoid those limits, that the turbocharger is not weak and the turbocharger is not very powerful. It has to be optimized in this case. But how we can do this matching exercise, شباب? So for simplicity, first of all, we can just consider take away the intercooler and the wastegate. Intercooler, which is after the compressor here, we should have intercooler. I will just exclude it from this cycle. Okay, which its function is to do what, شباب, the intercooler? Khalid, the function of the intercooler after the compressor. What its function? The function of the intercooler that should be after the compressor. After compressing the air, we should pass it through intercooler in order to do what, شباب? In order to cool down the air, to reduce its temperature. Then we can improve the density and we can improve the mass flow rate of air to the engine. But let's exclude them from the cycle for simplicity. And usually we have what is given for us in this exercise. We know about the brake power of the engine, required brake power. When you press the accelerator pedal in your car, so you decide about which brake power you want. And the engine should develop it. So we know the brake power. We know also at this brake power what will be the RPM of the engine. We can sense the RPM of the engine. We have the compressor map, by which here, يا شباب, the compressor map. This should be given with any compressor by the manufacturer. So if we have the mass flow rate at a given RPM, we can calculate the pressure ratio across the compressor. And also we have the turbine map, which we can use it. And we have also, شباب, engine map. Inshallah, I'll be talking about engine map, inshallah, in the next chapter when we talk about the engine performance. Engine map, يا شباب, give us the value. Here is the engine map. Engine map for any engine. All of these data points, يا شباب, are stored inside the ECU, which give you the value of brake main effective pressure. We said the brake main effective pressure is the brake power divided by the displacement volume. So it gives us the value of the brake power at a given engine RPM and for different value of brake specific fuel consumption. Brake specific fuel consumption with m dot fuel divided by the brake power. So if I have the brake power and I have the engine RPM, which we said they are given in this case, engine RPM and the brake power are given. Then using the engine map, I can get the value of brake specific fuel consumption. Brake specific fuel consumption, which is m dot fuel divided by the brake power. So I can get the value of the mass flow rate of fuel. So when the engine at a given, when you press on the accelerator pedal, the engine will decide, will know about the brake power required in this case. And it will go to the RPM sensor, it will sense the engine RPM. So it will go to this map and it will determine actually the value of mass flow rate fuel that is needed in this case. Okay, so this is actually what we know. We need to find, for the matching point, we need to find the compressor pressure ratio, the turbine pressure ratio. We need to get also the fuel to air ratio into the engine. And we need to get the temperature T3, decide about when we have to open the exhaust valve. And we need actually to get the turbine revolution, the shaft revolution of between the turbine, connecting the turbine and the compressor. The procedure here, Shabab, is just it can go this way. Just I will guess the value of compressor pressure ratio. And as I told you, Shabab, again, this is at the design stage. So if you have your car, it's already has been designed. Okay, but you can even, Shabab, if your car is not turbocharged, you can design yourself a turbocharger for this car. Okay. So those are the steps in this case, but you have to be able actually to insert the data. All of the operating point has to be matched with the ECU of the car. And I think that cannot be done unless you have a contact with the car manufacturer. Okay, but this matching, Shabab, at the early stage, when I have an internal combustion engine and I want to add a turbocharger. Okay, so I will guess the value. I need to get all of the operating conditions. So at each operating point, I will be just doing actually all of this procedure. So usually it is done, Shabab, using computer codes or something. So I will start with the compressor pressure ratio, just assume a given value. We set the limit, Shabab. The limit is 3.5. So I can guess value, let's say 2.5 or something, compressor pressure ratio. Then I can calculate the temperature T2. How we can get it, Shabab? So let's say we set the efficiency of the compressor is the actual, the isentropic work divided by the actual work. Isentropic work, which is m dot air, CB air multiplied by T2S minus T1, divided by actual, which is m dot air, CB air multiplied by T2 actual minus T1. M air, CB air will go together. If we took T1 as common, from up and down, will go. So T1 here will go and we'll have 1. It will be T2S over T1 and T2 actual over T1. So the efficiency of the compressor will equal to T2S over T1, which is the compressor pressure ratio, to the power K minus 1 over K, minus 1 divided by T2 over T1 minus 1. So if I need to get the temperature, I have assumed this value. Let's say it is equal to 2.5 from the initial state. Then from this equation, Shabab, I can get what? I can get the temperature T2 in this case. Temperature T2, which is the temperature at the outlet of the compressor. Then we can calculate the intake air density to the engine. Rho M, which will equal to B2 divided by R multiplied by T2. I have compressor pressure ratio, which is B2 over B1. We have already the value of B1, which is atmospheric. Then I can give the value of B2. Okay, just substitute here B2, and using this equation, we can get a relation for T2, and we can calculate T2. Then we can calculate the density of air at the inlet of the compressor, at the inlet of the engine. Then we can say mass flow rate of air, Shabab, will equal to what? The density of air multiplied by the displacement volume multiplied by the volumetric efficiency. Volumetric efficiency is the ratio between actual mass flow rate of air and the theoretical mass flow rate of air. So if we know the density, then we are able to calculate the mass flow rate of air. So I've calculated the mass flow rate of air. Then in this case, I will take this mass flow rate of air and the compressor pressure ratio and go to the compressor map, which should be given here. at a given mass flow rate, given pressure ratio, then I can decide about the RPM in this case. The N, which is the RPM of the turbocharger. I will get the value of the RPM of the compressor in this case. Okay, using those known value. And I will go to the engine map, as I told you, at a given mass flow rate of air in this case. Engine, we have the brake power, we have the RPM, then we can calculate the value of mass flow rate of fuel. Okay, mass flow rate of fuel, we can get the value of brake specific fuel consumption, which is m dot fuel divided by brake power. Knowing the value of RPM and the brake main effective pressure, we can get the brake specific fuel consumption and we can get mass flow rate of fuel. We have mass flow rate of fuel and mass flow rate of air, then we can calculate the fuel to air ratio. Okay, so now Shabab, we have the compressor in this equation. We have assumed the compressor pressure ratio, and we have calculated based on that the mass flow rate of air, and we have calculated the fuel to air ratio. Okay, now what is needed is to calculate the temperature T3 in this equation. T3, which is the temperature when the engine opens the exhaust valve. Like when the engine opens the exhaust valve, the temperature of the exhaust gases should be T3. From where we can calculate this T3, we have to make also develop an equation which is energy balance for the engine. We got two equations for the compressor. This is the equation, and the other equation is the RPM is the same. For the engine itself, we have to make also balance, engine balance. This is our engine. What is coming to the engine is the fuel. Also we have air coming to the engine. Some heat is transferred, fuel lost to the cooling water. And this engine can provide us the indicated power inside the cylinder. Indicated power, Shabab, the difference between indicated power and the brake power is the friction loss power. And the friction loss power is defined in terms of mechanical efficiency. So the mechanical efficiency of the engine is equal to the ratio between the brake power divided by the indicated power. Or the indicated power will equal to the brake power divided by eta mechanical of the engine. Eta mechanical is a well-known value. Brake power also is known for an engine. Then we have the indicated power. This is actually the output power of the engine. And in addition to this, Shabab, out of the engine, we should have what? We should have the exhaust leaving at temperature T3. But let's apply energy balance here. Let's take a control volume, apply the first law of thermodynamic energy in is equal to energy out at a steady state. So we can say m dot fuel multiplied by the heating value. This is the fuel energy plus m dot air coming into the engine, Cv air, multiplied by T2. T2 we have calculated. That should equal to the heat lost to the cooling water. We can calculate it. So this value is known. Plus the brake power, which is known, divided by eta mechanical of the engine, plus m dot exhaust, which is m dot air, plus m dot fuel, Cv gas, multiplied by the temperature of the gases leaving, which is T3 in this case. Okay, so let's look at this equation, Shabab. Here, this is the balancing equation. Based on this equation, we have all variables are known value. Then we can get the temperature. T3 in this case. Sorry, Said. So please unmute yourself. So this is, I can get the temperature T3. Once we have the temperature T3 and we have mass flow rate of the exhaust gas, which is mass flow rate of fuel plus mass flow rate of air, go to the turbine map. We have the mass flow rate. We have in this case also the RPM of the turbine should be the same as the RPM of the compressor. Then we can get the pressure ratio across the turbine in this case. So the pressure ratio, the turbine pressure ratio can be actually calculated using this equation. We have T3, we have fuel to air ratio. We have also the compressor pressure ratio we have assumed. Then using this balancing equation, we can get the turbine pressure ratio. Then we can take this turbine pressure ratio, Shabab, and go to the map. Sorry, we have to go to the turbine map in this case with this turbine pressure ratio and with the value of the mass flow rate of the exhaust, which is mass flow rate of fuel plus mass flow rate of air. Then we can get the value of the turbine RPM in this case. But this value, Shabab, of the turbine RPM should equal to the compressor RPM, which we get from stage number 3, step number 3. But usually when you assume the compressor pressure ratio, you will not from the first shot cannot get actually the same value. Usually you will find this value is not equal to the value of N of the compressor. Then in this case, I will go back to step number 1, assume a different value of compressor pressure ratio, and go through all steps until you have actually the RPM of the turbine is the same as the RPM of the compressor in this case. And that should be actually the matching point that matches the operation. All of the component in the system, the turbine, the compressor, and also the engine in this case. And then once we have the temperature T3 that we have calculated that can have the RPM of the turbine is the same as the RPM of the compressor. Once we have this T3, so the engine will decide actually when the engine should open actually the exhaust valve in this case in order to have this temperature T3. And we have to be precise, Shabab, about the valve operation in case of turbocharger system. The valve should be actually operated properly because we cannot open the exhaust valve too early in order to have high pressure, exhaust pressure P3 and high temperature T3. In this case, we will improve the operation of the turbine because we have higher pressure, high temperature at the end. It will provide higher pressure ratio across the turbine. But usually if you open the exhaust valve too early, that means in this case we are losing part of the pressure during the expansion stroke. We are losing part of the expansion work in this case. And we have to optimize the operation of the exhaust valve. Just we can open it at the value that will give actually a temperature of the exhaust gases equal to T3, which we have calculated based on this exercise. Okay? This is what will happen if we open it early, the exhaust valve. It will result in higher exhaust pressure in this case. But higher exhaust pressure, Shabab, if the exhaust pressure actually is too high, as I told you, we may lose part of the expansion work in this case. Just we need to optimize this operation. Also, we need also precise timing between the exhaust valve and the intake valve opening in order to control actually the intake pressure and the exhaust pressure. And we have, Shabab, an overlap period in which we have both the intake valve and the exhaust valve are opened at the same time. So the exhaust valve open before the bottom dead center in the expansion stroke, and it is open during the exhaust stroke from the bottom dead center to the top dead center, and it does not close actually until the top dead center. And in this time we should have the intake valve is opening. Intake valve open before the top dead center in the exhaust stroke, and then it continue opening during the intake stroke from the top dead center to the bottom dead center. There is an overlap period, which is actually this period here. This is the overlap period in which we have both the intake valve and the exhaust valve are opened at the same time. That means, Shabab, if we have the compressor, the turbocharger is very weak at lower RPM. Mass flow rate is low to the compressor, to the turbine. That means the compressor pressure ratio will be low. That means in this case the intake pressure will be low. And this, Shabab, may result actually in very low. In this case, actually, if the intake pressure is very low, and it is less than the exhaust pressure, in this case, this will prevent actually the fresh charge from incoming into the engine, because the intake pressure is lower than the pressure inside the cylinder during the overlap period. So the intake charge will not be able to get inside the engine. So you can imagine, turbocharger may result in very low pressure if you are not matching the operation very well. The pressure in the intake manifold may be less than the pressure inside the cylinder. And in this case, the fresh charge will not be able to get inside the engine in this case, and the engine will stop. But what will happen, Shabab, if the intake pressure is too much high? The turbocharger is actually very powerful in this case. So what will happen in this case, Shabab? The intake pressure is much higher than the pressure inside the cylinder while the overlap period, when we have both intake and the exhaust valve are open. So what will happen in this case, Shabab? But what will happen in this case, Shabab? So if the intake pressure is much higher than the pressure inside the cylinder, while the overlap period, when we have the intake valve and the exhaust valve are open at the same time, that means the flow of incoming fresh charge will just go inside the cylinder and it will be leaving actually through the exhaust valve. Then in this case, if we have higher intake pressure, very powerful turbocharger, part actually of the fresh charge will be just actually exhausted through the exhaust valve during the overlap period. So we have to do a shabab, we have to do precise actually design of the turbocharger with the engine. They have to be matched together in order to have the best performance in this case. But in case of supercharger, we don't have a turbine, so we don't need any for early opening of the exhaust valve. Usually we delay the exhaust valve opening so that we can benefit the expansion power in this case. Because we don't need actually, we will not be recovering the heat from the exhaust gases in this case through a turbine. We don't have a turbine in case of supercharger. The compressor is driven by part of the power of the crankshaft. So in this case, we don't need to early open the exhaust valve, but we have to have precise timing actually for the intake and the exhaust valve during actually the overlap period. In this case, the overlap period, ya shabab, this is very important. The overlap period, the period at which the intake and the exhaust valve are opened at the same time, will be reduced in case of supercharger compared to the case of turbocharger. You can see the width of this blue line is bigger in case of turbocharger compared to the supercharger in this case. Why is this, Shabab? Why we reduce the overlap period in case of supercharger? Why we do that? As I told you, in case of increasing the pressure, intake pressure too much, and during the overlap period, the incoming fresh charge under high pressure will be just to go inside the cylinder through the clearance volume. It will scavenge the exhaust gases, and the part of the intake actually charge will be just thrown through the exhaust valve in this case during the overlap period. And that's why we have to reduce the overlap period in this case, in case of supercharger, to reduce the amount actually of losses in the intake charge during actually the overlap period of the intake and the exhaust valve in this case. طيب here شباب, some are modern design of the turbocharger. We have a challenge in the turbocharger, as I told you, that it increases the temperature of the combustion and the pressure inside the combustion chamber. And this will apply actually if we have higher temperature. First of all, there is a possibility of knocking in case of gasoline engine. And second, we may have emission, like NOx emission. The thermal NOx actually result from high temperature combustion. So in this case, Shabab, this will interfere the operation of the turbocharger, because having turbocharger will result actually in higher engine emission in this case. And as I told you, the trend those days is to use actually the low temperature combustion. We have converted from non-premixed to premixed combustion in order to lower the combustion temperature and reduce the NOx emission. Now, if I am using actually a turbocharger, in this case, I am increasing the mass flow rate of air and mass flow rate of fuel, and I am burning in this case at higher combustion temperature and higher combustion pressure, and this will result in higher emission in this case. So this is the challenge that we are facing with using turbocharger or supercharger, mainly turbocharger. Okay. But what are the solution? We have some solution. We may have actually a kind of electrically assisted turbocharger. In this case, the turbine is connected to the compressor, and we have a wastegate. But this turbine, Shabab, is connected to an electric motor. This electric motor can work as a motor or as generator. So during actually, in case at full power, at full load condition, usually we have higher amount of the exhaust gases. It will drive this turbine. The turbine will drive the compressor, and the excess power will be actually used to generate electrical power through the electrical generator, and this power will be saved in the battery. But what will happen at lower RPM? Lower RPM, the mass flow rate of the exhaust is low. So the turbine will not be able to generate enough power for the compressor. So in this case, the battery will just drive the electrical current to the electric motor. It will work as electric motor in this case, and it will drive this shaft, and it will run actually the compressor at lower RPM in this case. So the benefit from this design, Shabab, will increase the airflow rate at low engine speed. We said at low engine speed, the turbocharger is suffering because we don't have enough amount of exhaust gas to generate power for the turbine to drive the compressor. But in this case, using electrically assisted system, it can enhance the performance of the turbocharger at lower RPM. And we have auxiliary electric power output during actually the full load in this case. we can save it in the electric battery, and then we can use it actually at lower RPM in this case. This design is still we have a waste gate, because using at full load condition we have excessive amount of exhaust gases, so we need the waste gate. However, we have electric motor here, but still we need waste gate in this case. So that we can improve the design a little bit more, we can just get rid of actually of this waste gate, just leave it, and totally the turbine will not be connected to the compressor. Turbine will just take the exhaust gas from the engine, it will generate shaft power, and this shaft power will be connected to an electric generator to generate electrical power. This electrical power will be saved at full load condition, will be saved in the battery. Part of it will be saved in the battery, and the other part will be driving an electric motor. This electric motor will be driving the compressor. And at part load condition, usually the power coming from the turbine is low. So in this case, the battery will be driving the electric motor, supply the electric power to drive the electric motor. Then the electric motor can drive the compressor in this case. The benefit here, Shabab, we have decoupling between the compressor and turbine. Compressor and turbine are not connected here. They are separated from each other. And this, Shabab, will just reduce here the optimizing steps, the exercise to have matching. In this case, we don't need actually the turbine map. We don't need the compressor map because they are not connected together. Just we have a battery in this case, and the electric motor will drive the compressor. Okay. We have auxiliary power output, as we said. We can have electrical power. And in this case, Shabab, we don't have turbo lag. We said in case of turbocharger, there is a lag because actually it needs some time to generate exhaust gases and drive the turbine to drive the compressor. Then we can have boost in power. But in this case, the turbine is not connected to the compressor, and at part load, the compressor can be driven through the battery, through electric motor, which can take the electric power from the battery in this case. So we don't have turbo lag. So the turbocharger in this case will be perfect, even at part load condition or at lower RPM. Here, Shabab, you can see some different reason for turbocharger surging, which is the stopping of the turbocharger. As I told you, Shabab, when we have this matching process, we get all of the operating condition at all loading condition from part load to full load, and all of this data will be stored in the electronic control unit. Then the engine will not be going actually beyond this limit. Okay, but in some severe situation, if you have blockage in the exhaust system, that will cause back pressure on the turbocharger and it will stop the operation of the turbocharger. If you have fault in the fuel system, maybe blockage in the fuel line or the pump is not working, so that means in this case the operation of turbocharger will be stopped. If you are changing rapid change actually from the part load to full load, or deceleration from the full load to you stop the car actually, just like in case of accident or something, the car has been stopped. So in this case, the turbocharger system also will be stopped in this case. Or if we have engine operation at overload, you are running your car at speed very close to the limit. So in this case, the turbocharger also, you may have problem with the turbocharger. So just be careful, if you have a car, turbocharged car, don't say I have a very powerful car. Yeah, it's okay, it's very powerful, but when you go to the limit, it will be powerful and this power will come back on you. Okay. So please be careful. This turbocharged car is a powerful, but at overload operation, you are putting yourself in a severe danger in this case, okay, or a real danger in this case. So those are some reasons, Shabab. Here is a comparison between super and turbocharger. We said in case of supercharger, it takes part of the power of the crankshaft. That's why, Shabab, the brake power will equal to the indicated power minus the friction loss power in the piston minus the power required to drive the compressor in case of supercharger. But in case of turbocharger, the difference between the brake power and the indicated power is the friction loss power only, because the turbine is just operated by the exhaust gas. Regarding the brake power, for the same intake pressure and the intake temperature, turbocharger utilize the exhaust gases. So it should have higher, in this case, it should have higher brake power, because in case of supercharger, it just consumes part of the brake power. So it will result in lower brake power of the engine. The cost is cheap in case of supercharger, but it is more expensive in case of turbocharger, because we have additional devices. Lagging in case of supercharger, it can respond at part load condition, but there is lag in case of turbocharger because we need some time to generate power. The use is actually is to enhance the brake power for both of them. And the spark ignition and the compression ignition engine, mostly we use supercharger with the compression ignition engine. And in case of gasoline engine, we can use both. But in case of gasoline engine, usually the gases are at high temperature, then we can utilize actually those gases in case of turbocharger. But can we use a شباب get benefit from both of them at the same time, turbocharger and supercharger? Yes, we can use a turbocharger with a compressor. We can connect to the compressor to the crankshaft to drive the compressor at part load condition or at lower engine speed. And at higher engine speed, we can just drive the compressor through the turbine. So we can combine them together in one engine. But what about شباب used supercharger or turbocharger in gasoline or diesel engine? Which one is preferred to use turbocharger or supercharger? Gasoline or diesel?
Gasoline.
Not really شباب, because there is limitation in gasoline engines that we may have engine knocking. Higher temperature combustion, higher pressure combustion may result in engine knocking. It is used in gasoline engine شباب, but used precisely or carefully in gasoline engine to avoid engine locking. But in case of diesel engine, we don't have limitation for the compression ratio. So usually شباب, the supercharger and turbocharger are used extensively actually in the gasoline, in the diesel engine. And diesel engine شباب are used in not only in the car. We have different uses for compression ignition engine, diesel engine, in different application for auxiliary power generation. We may have big diesel engine in order to drive a generator to generate electrical power. And those actually are used in rare region where we don't have a source for electricity, or in locomotive application, or also in marine engine we use diesel engine. In this case, those engines should be turbocharged or supercharged in order to increase their power. So we have different application. Okay, so that's